You ever think about how wild it is that we all just run pip install or npm install and hope for the best? One command, and we are letting random internet code into our machines. And we do this daily across almost every language ecosystem: Python pip, Nodes npm, Ruby gems. Thing is, these packages managers usually default to pulling from public registries, and unless you have locked the thing down properly, the trust can be hijacked. In today's episode of the Snakebite series, we are talking about one of the cleverest bugs to ever hit the software supply chain, a technique that got code running on Apple servers, Microsoft Cloud builds, Shopify CI, and it all started with a few suspicious package names. Back in 2020, a security researcher named Alex Birsan, hope I'm pronouncing it right, was bug hunting, digging through GitHub, helping a friend test PayPal. They found a Node.js project that had a package.json file listing a mix of public and internal dependencies. Some packages were private, like internal to PayPal, and didn't exist on npm. That raised a big question. What would happen if someone just published those same package names to npm before PayPal did? Would their build system pick up the public one instead of the internal version? So, Alex took the idea and ran with it. He looked at those internal sounding package names, stuff like PayPal-internal-auth or corp.logger, and realized if they weren't on npm, they were fair game. He recreated those packages' names and pushed them to public registry, but instead of anything harmful, each package came with a tiny script, something like a pre-install or post-install hook, and that script, it quietly collected some basic info from the machine it was running on. It means if anyone install this code on their machine, this script is going to run in their local machine. So what this script going to do? Things like the username, the host name, the working directory. It's going to fetch that. Nothing personally invasive, just enough to identify the install for this testing purpose. But here's the smart part. It didn't try to exfiltrate the data through HTTP or anything obvious. It used DNS. Why? Because DNS traffic tends to fly under the radar. It's allowed out of most corporate walls, so the data was hex encoded and sent as part of a DNS query like abcd123.user.pkg.project.attacker.com, something like that. That query would hit public DNS resolvers and eventually reach Alex's custom name server, which just logged the incoming request. Just a quiet ping letting him know, hey, this package just got installed on someone's machine. And then the ping started rolling in. It wasn't just one off, the thing worked across the board. Packages started getting installed on developer laptops, internal test servers, automated CI/CD pipelines, cloud build environments like Azure DevOps and Jenkins. In some cases, the installation happened within minutes of the upload. That's how tightly coupled some build systems are to public registry. Because we do this often, right? And what about the companies? Some big companies like Microsoft, it was affected by their Office 365 pipeline. Apple, their internal system, installed that package. Shopify, their Ruby build server, executed the code. PayPal is the one where it all began. And Netflix and Uber, they were also vulnerable. These weren't fringe components either. Sometimes these installs happened inside auth systems, CI infrastructure, or services related to identity. The bug bounty payouts reflected that risk is $30,000 from Shopify. Same for Apple, $40,000 from Microsoft, their highest zero reward, and another $30,000 from PayPal. And almost all of them were at maximum reward tier for those programs. Dependency confusion wasn't just valid, it was critical. So, you must be thinking why this works. At the core of this attack is one simple question: how does your package manager decide where to get a package from? The answer for most ecosystems is not very carefully. Let's take pip, for example. A lot of teams use hyphen hyphen extra hyphen index hyphen URL to add their private registry alongside PYPI. The idea is use the internal one when it exists, but fall back to PYPI for public stuff. The problem is pip doesn't enforce which registry should be trusted more. If the package exists on both, it installs a version with the highest version number. So if your internal registry host internal-lib equals 1.2.0, that is the version number, and the attacker uploads internal-lib equals 9999.0.0, obviously it's a way higher version number, to PYPI. And guess what? Pip grabs the attacker version because it's a higher version. So it thinks, okay, this is the most updated version, let's grab it. NPM has a similar flaw. If your .npm-rc isn't scoped correctly or uses a merged registry like JFrog Artifactory, it might pull in public packages even when an internal one exists. Azure Artifacts and Artifactory both allow mixing public and private sources, unless explicitly configured. They'll do the same thing, choose the higher version number even if it's from the public side. What made this whole attack even more scalable was how easy it was to find private package names. These internal names are everywhere if you know where to look. Some of them leak through GitHub commits, public package.json files, or requirements.txt files, or from build artifacts like minified.js files, forums, docs, Stack Overflow posts. You can check them out, you just have to give them the time, like Alex did. But the real goldmine are JavaScript files. During a build, some organizations accidentally embed their internal package.json directly into the public JS bundle, especially in enterprise React or Angular apps. Sure, we have seen that a lot. That means dependency names and sometimes version numbers get pushed live without anyone noticing. Researchers used automation to scan millions of domains, parsing .js files. For require function calls or embedded pods, they surfaced hundreds of internal dependency names. Even you can just open up a JS file and you can manually look for it as well, or you can automate this process as well. So just like that, one of those names were found and they just had to register it publicly. And once uploaded, it's just waiting game. Now that we have talked about the bug and how this all happened, let's talk about how to fix it. So how do you stop this from happening? There's one-click patch, but there are ways to lock things down. Here's the short list. Use --index -URL instead of --extra -index -URL in pip. This tells pip to only use your private registry. So extra -index is where confusion creeps in. Don't use that. The second step is scope internal packages. In NPM, use something like at your org/internal-lib. Scoped packages must come from defined sources. So keep that in mind. And the third step would be block public registry fallback. If your build tool or registry proxy allows public fallback, disable it. Another way is pin versions and use log files. Log down exact versions and sources using package-log.json or pipefile.log or similar. And also, Microsoft even published a white paper called 3 Ways to Mitigate Risk When Using Private Package Feeds. If you want to dig deeper, thought to point that out for people who are developers here. So, dependency confusion didn't need a 0-day, just the ability to upload to a public registry and wait. It wasn't a breach in the traditional sense, but it did sounded like it. It was a failure in how developers and systems decide what to trust. Because this isn't a one-time thing, it's a class of bug, a whole category of mistakes that can hit anywhere in the software supply chain. So whether you're building, deploying, or hacking, it's worth double-checking how your packages are resolved. And this is something you can try while bug bounty hunting as well, with proper authorization, of course. So guys, that's it for today. If you found this episode cool, don't forget to share it with your friends. Thanks for listening, and I'll see you in the next one.